Every time you plug in your phone, a silent struggle is happening inside the battery. We often talk about lithium ions and electrolytes, but there is a hidden component that determines whether your battery lasts for years or dies in months. The secret isn't just the chemistry, it's the glue. Specifically, a polymer binder that holds the active materials together. It's only 10 nanometers thick, making it virtually invisible to even our most powerful microscopes until now. When this glue fails, the battery's internal structure literally falls apart. But because we couldn't see it happening, engineers were essentially flying blind, trying to fix a problem they couldn't even visualize. To understand why this happens, we have to look at how batteries are made. It starts with a process called slurry mixing. Imagine a giant industrial blender filled with active materials, conductive carbon, and that critical polymer binder. This slurry is coated onto metal foils and dried. As the liquid evaporates, the binder is supposed to form a perfect uniform network. But in reality, it often clumps together or migrates, creating weak spots in the battery's foundation. Think of it like building a skyscraper where the cement is unevenly distributed. On the surface, the building looks fine, but the moment you put it under pressure, the cracks start to form where the glue is thinnest. For years, the 10 nanometer polymer binder was the invisible failure point of modern batteries. It's so thin that standard imaging techniques like X-rays or electron microscopes simply couldn't distinguish it from the other materials in the mix. This lack of visibility meant that when a battery's performance dropped, researchers had to guess why. Was the lithium plating, was the electrolyte decomposing, or was the binder simply letting go? The engineering challenge was immense. How do you see something that is only a few dozen atoms wide, buried deep inside a dense, opaque metallic sandwich? The answer came from a brilliant team at the University of Oxford. In February 2026, researchers published a paper in Nature Communications that changed everything. They developed a revolutionary staining technique that finally made the invisible binder visible in high-definition 3D. By using specific chemical markers, they were able to dye the binder without changing its physical properties. This allowed them to map the entire structural network of the battery for the first time in history. This wasn't just a new image, it was a new way of seeing. It revealed that the binder wasn't just a passive glue, but a dynamic architecture that was constantly shifting and breaking during every charge cycle. The implications are massive. By understanding how the binder fails, we can finally engineer batteries that don't just store more energy, but can handle the extreme stresses of ultra-fast charging without falling apart. We are moving from a world where battery health is a black box to one where we can see every single nanometer of the structure. And the secret to this new vision lies in two specific elements: silver and bromine. But before we get to the performance data, we need to understand the clever engineering behind these markers. How do you tag a polymer without ruining the very battery you're trying to study? To see the binder, the Oxford team had to find a way to make it stand out against the dense background of the battery. They turned to heavy atoms, specifically silver and bromine, to act as chemical beacons. These atoms are much heavier in terms of electron density than the carbon and hydrogen that make up the polymer. When an electron beam hits them, they scatter the electrons much more effectively, creating a high-contrast map. It's like trying to find a clear fishing line in a swimming pool. By attaching tiny silver bells to the line, you can't see the line itself, but you can see exactly where it is by looking for the bells. The genius part was how they attached these markers. They used a process called staining, but not like you'd stain a piece of wood. They engineered the polymer binder to have specific chemical hooks that only the silver and bromine would grab onto. This selectivity is crucial. If the markers attached to the active material or the electrolyte, the whole image would just be a blurry mess. By only tagging the binder, they isolated the battery's skeleton. This allowed the researchers to use a technique called energy dispersive X-ray spectroscopy, or EDS. By scanning the sample, they could detect the unique X-ray signature of the silver and bromine at every single point in the electrode. The result was a 10 nanometer resolution map. To put that in perspective, a human hair is about 80,000 nanometers wide. We are looking at the glue of the battery at a scale where we can see individual polymer clusters. For the first time, researchers could see binder fragmentation. As the battery charges and discharges, the active particles expand and contract like a breathing lung. This mechanical stress eventually snaps the 10 nanometer binder threads. When the binder snaps, the particles lose their electrical connection. It's like a wire being cut in your house. The power is there, but it has no way to get to the light bulb. This is a major cause of capacity loss over time. But the Oxford team didn't just see the damage, they saw the cause. They discovered that the binder doesn't fail randomly. It fails in specific patterns based on how the slurry was mixed and dried months earlier. They found that in fast-charging batteries, the binder tends to migrate toward the surface, leaving the core of the electrode brittle and prone to cracking. This inhomogeneity is the silent killer of fast-charging performance. By visualizing this fragmentation in real time, the team could finally start testing new binder architectures. They weren't just guessing anymore, they were engineering at the nanoscale with perfect vision. This breakthrough represents the aha moment for battery researchers. They realized that the physical structure, the way the glue is distributed, is just as important as the chemical formula of the battery itself. It turns out that the bottleneck for fast charging wasn't just how fast ions could move through the liquid, but how well the physical skeleton could hold the battery together under the pressure of that movement. With this new understanding, the team set out to redesign the battery from the ground up, and the results they achieved were nothing short of staggering, especially when it came to internal resistance. Armed with their 10 nanometer maps, the Oxford team redesigned the physical architecture of the electrode. Instead of a chaotic mix, they created a hierarchical binder network that provides maximum support exactly where the stress is highest. This new structure acts like a shock absorber for the battery. As the particles expand during fast charging, the binder stretches and flexes without snapping, maintaining perfect electrical contact throughout the entire electrode. The result of this physical optimization was a massive drop in internal ionic resistance. When ions can move freely through a stable structure, the battery generates less heat and can accept a much higher current. The performance data is incredible. By optimizing the 10 nanometer binder architecture, the researchers recorded a 40% reduction in internal ionic resistance. In the world of battery engineering, a 40% improvement is almost unheard of. This 40% drop is the key to ultra-fast charging. Resistance is what causes batteries to heat up when you charge them quickly. By cutting that resistance, you can pump in more energy without the risk of thermal runaway. This enables charging speeds that were previously impossible. We're talking about taking an EV from 10% to 80% in roughly 5 minutes, about the same time it takes to fill a tank of gas. But the benefits go beyond just speed. Because the binder is no longer fragmenting, the battery's lifespan is significantly extended. The Oxford team's data shows that these optimized cells can handle thousands of fast charge cycles with minimal degradation. This solves one of the biggest hurdles for electric aviation and heavy trucking, where batteries are put under extreme stress and need to last for years to be economically viable. The 10 nanometer staining technique has effectively turned the battery from a wear item into a permanent component of the machine. It's a shift from disposable tech to truly sustainable engineering. The next step is scaling this discovery from the lab to the factory. Manufacturers are already looking at how to integrate silver and bromine markers into their quality control processes to ensure every battery has a perfect binder network. By using these markers during production, we can catch structural flaws before the battery ever leaves the factory. It's like having an X-ray vision for the assembly line, ensuring 100% reliability. This technology will eventually find its way into everything, from the phone in your pocket to the grid-scale batteries that power entire cities. The invisible glue is finally getting the attention it deserves. The University of Oxford's breakthrough reminds us that the biggest problems are often solved at the smallest scales. By mastering the 10 nanometer world, we've unlocked a new era of energy storage. Next time you charge your phone in minutes or see an electric plane take to the skies, remember the invisible 10 nanometer glue and the chemical beacons that finally brought it into the light. The future of power isn't just about better chemistry, it's about better architecture. And now that we can see it, there's no limit to how far we can go.